Well, welcome guys, and obviously this is not that far. We are in Melbourne in the CBD in Carlton, but this is a lovely introduction, and I'm glad that you're spending your valuable time at this show and coming to listen to me. So we'll try to make it as entertaining as possible, probably not to that extent. I've been talking the whole day, so I'm running out of steam a little bit. But let's try to understand what is additive manufacturing all about. Why do we care about metals? Obviously, other materials are as important, but I will not be spending too much time talking about polymers and ceramics. However, if we look at the typical part on the left-hand side that many of you will see maybe at some stage, and because you're here all at manufacturing show, you will know that traditional manufacturing or conventional often requires technologies such as CNC machining or forgings and others. These technologies have a lot of advantages, and most of the part nowadays are still produced with these technologies. But obviously, if we compare the part on the left-hand side with the one on the right-hand side, they have the same function, but they are very, very different, right? And we can all recognize that. However, the technologies that are required to produce the part on the right-hand side are quite new. And this is what additive manufacturing is all about. It's turning your feedstock material, typically powder or wire, into a functional part that can fulfill your requirements as an industry, right? And if you look at the landscape is quite large. So lots of different processes have been developed over the last 25 years. This is a schematic drawn by some of our colleagues from Germany. And what I will do today is I will cherry pick a couple of those technologies and show you what we do here locally in the country, and particularly obviously at RMIT, but there's many other great places, your Swinburne, your Monash, universities in New South Wales, in Western Australia. All of us moved into that space in the last 10 to 15 years. I will particularly talk about powder bed fusion processes. I will touch on the VAM technology, which is the wire arc additive manufacturing, and each time try to give you a small case study where we can see a direct benefits for the industry, right? So let's start with why do we care and what kind of industry is looking for. Actually, if you look at the traditional manufacturing, the additive manufacturing is the one that's still growing almost 20% year to year. And this is significantly higher and as any other industry. Of course, the reason for this growth is that it's still a relatively new industry, so it's much easier to grow when they're a new industry. But this particular slide highlights that many of the industry sectors can benefit from additive manufacturing. That includes your energy sector, your dental, your medical, automotive, and aerospace. And they're all projected to continue to grow in those double-digit areas. So first, let's look at one of the technology that we use a lot, and we were probably the first institution in Australia to bring laser powder bed fusion to Australia. And this is a process where you can see a short video of magical lasers working together, in this case 4 lasers, trying to fuse a very fine powder to produce a part. If you look at the schematic, obviously we have to take a very fine powder, which is roughly in the size, half of the size of the typical sand that you find on the beach. You spread this powder on the build plate in a thickness of 60 micron. You melt it selectively, and that produces one layer. If you put the powder on top of it and you repeat that over and over again, at the end you are able to remove a nice part that will have a really great quality. And that's kind of the part that you saw at the first slide. Okay, so really great technology. The other technology, and I'll come to case studies a bit later, that I want to talk about again, that we use a lot in our facility is laser-directed energy deposition. So if you want to go to larger parts, it gets more complex because the previous technology had some limitation in the build plate. So if you want to build it bigger, you might use the same powerful lasers, wire or powder, and spread it and melt it on demand. And the example again of the video that we see here demonstrate what happens still on each layer. You can start producing parts of different geometries and different complexity. However, now you're much less restricted on the size of the parts. And finally, if this is still not large enough, so in this technology, we're typically talking about parts of several meters. If you want to go even higher, then we go to bio-arc additive manufacturing. So in this case, you have a robotic arm equipped with a torch, which is essentially a welding torch, and that torch melts a welding wire to produce parts. In our facility, we are able to get you parts up to 500 kilo. And this is mainly limited by the size of the robots, and particularly the robotic table, because obviously when you start producing complex 3D shapes, you need to be able to tilt this plate and you need to be able to position everything. So that's the main limitations. However, all of these three technologies have in common that we still produce parts in a layer-by-layer fashion. And we are looking at producing parts that are fit for industrial applications, all right? So this can be summarized if you look at the technology maturity levels of these technologies. This is a schematic that was produced by some of our friends in Germany. And you will see that many of these technologies that I mentioned, they're starting to move towards the right corner. So the right corner here means that we are either already industrializing this technology or very close to it, and the technology is mature enough to start producing serial production. And there's a number of companies that are in this space, including Siemens and Boeing and many others, that are producing now parts using this type of technology. So I'll try to highlight where the technology is at the moment, where we are moving towards, and then give you a couple of specific examples. So what we would like to see, and the current trend is that if you print something on demand in a layer-by-layer fashion, obviously the productivity and competitiveness to the existing technologies is a big question. Anyone coming to you and say, why should I be using additive manufacturing? They might have a business case for a complex part, but they still care about how competitive is your pricing, right? So we need to work towards improving that. Material selection was another and continues to be a major point of research where we spend a lot of time, because not all materials that are developed for castings or forgings or other technologies can be directly transferred into additive manufacturing. So the role of many of the research organizations is really to take this on board and develop new materials that sometimes are even better than the existing materials and can only work when you use them in additive manufacturing. We start seeing some wonderful things where we can tailor our material properties on demand. So you can envisage parts, let's say you're building a bike, where your bike might have a different strength and ductility depending on the location of the part. And that could be tailored to improve the damping capability or improve a strength if you're doing some mountain bike riding, right? And if you compare that to a traditional manufacturing, this is essentially impossible unless you break everything up in small parts and you start to combine them. And multi-material printing is another wonderful example that I will highlight when we talk about it. Okay, so let's look at what are the typical examples. And you'll see, for instance, here on the left side, if we start with Siemens, Siemens is producing lots of parts in the UK and putting them in service. You can see some examples from GE at the bottom, which is a very famous fuel nozzle, but there's also companies like SpaceX. So if you look at SpaceX, SpaceX would not exist nowadays if they did not have additive manufacturing, because additive manufacturing and particularly laser bed fusion allowed them to produce parts and iterate very quickly and come up with the designs. And in fact, I have a very nice example to demonstrate how the technology enabled them to completely change their design and gain a lot of advantages. I'll also like to highlight that example in the middle with a spinal implant. So it's not just about the general engineering. We are also helping a lot in the medical field. So most of the implant companies, particularly companies like Stryker, they all move towards producing biomedical implants on demand. They're still not bespoke, but they're able to produce them on demand and produce them in mass. So Stryker, for instance, printed over 2 million implants in the last 10 years, and they keep wrapping up their manufacturing. So meaning that it hopefully gives you a feel for the technology and how far the technology is. However, if you look at the numbers, we are still in a very small market. So we're still talking about 20 billion market, which is a really small fraction compared to the total manufacturing. But the projection is very positive. So we, even within the country here as Australia, we are very much interested in distributed manufacturing and starting to produce parts on demand. So because often in your general fields of engineering, you might be waiting for your parts to come from somewhere, US or Japan or UK, and that might take you 3 months, it might take you 6 months. We might be able to do this kind of things in a country very soon, already doing that, right? I also wanted you to have some takeaway images of really fantastic application, and just to demonstrate how different this technology is. So here you're looking at a hypercar produced in the US. And obviously, if you look at the way the car looks, you recognize that many of the parts are 3D printed. They have organic shapes and they're extremely light and not just functional, but typically the performance of these parts is improved substantially. And you are able, if you are working in the industry, you're able to tap into this type of innovation even nowadays already in Australia. I mentioned before SpaceX, and I saw that this will be a great image to demonstrate the power of additive manufacturing, because if you look at the left side, and this is the Raptor engine that SpaceX used in the beginning, this looks significantly different to the third iteration. And this is all enabled by additive manufacturing. So what did additive manufacturing do? It's actually allowed the company to consolidate many of the parts, print them as one, and also significantly change the design and functionality. We've obviously been working in this field for now over 15 years ourselves, and I want to give you some examples of positive impact of this technology in the country. So for instance, we worked with our defense forces to try to repair actual components. So here's an example of a landing gear shaft. And you can see in the video directly playing an example of how the surface gets repaired and prepared for post-cladding machining. And the main advantage, if you want to come to our facility and inspect these kind of parts, because it's not always easy to see it in the videos, that you end up with parts that you as an industry will never recognize that this was additively manufactured, right? So another wonderful example comes from a repair of large components. So in this case, a slurry pump. If you look at the applications of the slurry pump, you see that these parts get worn out very quickly, in less than a couple of months often. And if you need to reorder these parts, that will cost you quite a lot of money, and there's a significant delay in procuring these parts. So now we worked with Weir Minerals for a number of years now to try to utilize via arc additive manufacturing, one of the technologies that I mentioned before, to try to locally repair this type of parts. And I want to give you an example of what that actually means. So if you receive this kind of one part, you will realize that there's a lot of areas that needs your attention. You'll need to understand how you will prepare it for additive manufacturing, because you won't be just starting printing on top of that surface. It typically means that we rely on technologies such as 3D scanning to get a digital twin of that part. We often do some advanced modeling to understand how the part works. And we are lucky enough that we can obtain an original card and a worn part, and we can use them together, and just using some basic operations, then understand how the repair needs to work, right? And the technology is advancing that fast that if you've done it once, and it might take you originally some time, then all of this can be progressed. We can model the tool path generation for the part and end up with a part that we can send out back to the industry in a couple of days rather than waiting for these kind of parts for multiple months, right? Of course, what I should mention that what's not obvious from maybe from this image, that these parts weigh roughly 150 kilo. So we're not talking about small gadgets or widgets. It's a real engineering parts that are put back into service. And this is already happening in the country, right? Now, for many of the other parts that you can see when you walk around the show, and there's a significant corner of the show that deals with additive manufacturing, quite a number of companies, a lot of them are using laser powder bed fusion process. And this is the process that has the advantage that you're able to produce very fine parts and very intricate. However, the process is, of course, very complicated and requires a lot of knowledge. So if you're interested in this area, I encourage you to maybe download one of our chapters of the book. So we're quite happy to share all of the knowledge that we accumulated over the last 10 years. So you're able to access that directly from Elsevier and read about how the technology is developing, right? And in the last few years, we saw a significant uptake of this technology, particularly in Southeast Asia. In China, we have now significant number of manufacturers that are producing parts on demand. What makes it interesting is that our initial ideas about this technology were quite limited. We always thought that we will never go past couple of lasers. So the example you saw at the beginning, I showed you that in our facility, we're using 4 lasers within this technology. And we thought that was commercially the only viable system. However, if you go now into the market and you start asking about this type of technology, you can not only find printers with 12 lasers, there are companies offering this technology even with 64 lasers. So each of these lasers obviously is quite expensive, but the prices are going down. And the main idea, of course, is that if you have multiple lasers working, like you can see here, an example from Porsche, a German automotive manufacturer, you can start either printing the same part with a single laser, or sometimes you're printing a larger part using multiple lasers in the same time. So you're ending up increasing your productivity quite significantly. So you might ask, so why don't we see so much of it already in the industry? The main answer is this complicated graphics, right? If you look at the materials, and I know maybe most of you are here not material folks, but typically we're dealing with titanium alloys, aluminum alloys, and cobalt steel, nickel alloys. Those materials are materials that we inherited over the last, or developed in the last 100 years. Most of them are not developed for additive manufacturing. So our role is either to demonstrate that they can be used or adjust the alloys. And in fact, even within the last couple of years, we were quite lucky to develop some new materials, particularly in the titanium space, and Monash did that as well. And these alloys will enable completely new applications. The schematic at the bottom is perhaps a very nice demonstration where the future will take us, because normally when we deal with engineering materials, we're dealing with homogeneous or isotropic materials. They don't change in any of the directions. However, both the technology and the understanding of the materials is changing. So we're starting to be able to produce gradient structures where both the microstructure and the properties are changing depending on the location, right? And this is completely a game changer in the future. And I just show you an examples where this is already taken up partially. So for instance, NASA is using the multi-material ideas and trying to create liquid rocket combustion motors that have a copper alloy and nickel alloy in the jackets together in the same time. And that increases the capability of this type of materials. So in our facility at RMIT, we have a nice small bench test equipment that manages to do this as well. So you see on the small video two of different materials deposited in the same time and molten to create new types of composite structures. And examples on the right-hand side demonstrate what this kind of innovation will bring. So we're going to start to be able to combine different materials, particularly metallic materials, in a completely new way that didn't existed before, because this technology allows us to do that on each of the layers, right? So what does it take us as a country? This has been really recognized now by local governments and federal governments, and they funded an additive manufacturing CRC. So this was announced only a couple of weeks ago, and that CRC brings together all of the major universities across the country as a research partners, and a significant number of small, medium, and large businesses. These businesses already either are using additive manufacturing or considering to use that as their future development platform. Many of these companies are exhibiting here. So for instance, you might be able to go and see Additive Surgical. We have Additive Engineering here, and many others who are listed. So, and a lot of the innovation is actually shared outside of the country. So I might point out that, for instance, Conflux, which is a company that's just in Geelong, just this week opened a facility in the UK to bring the innovation from Australia in the area of heat exchangers to the UK market, right? So as I mentioned in the beginning, RMIT invested quite heavily in advanced manufacturing. We've been in this area for the last 14 years. And obviously we'll be very happy to work with you if you have any questions. But what is important that none of these technologies work in isolation. So it means that when you work in the manufacturing, you still need substantial capabilities in the subtractive manufacturing. You need to be able to inspect your parts. So you need microscopy and microanalysis facilities. You need testing facilities if you're developing new types of products. So we will be very happy to accommodate any of your keen interest in parts and see if we can develop something. So this is part of our team, and I'll be very happy to take any of the questions if you have on additive manufacturing. Thank you guys for listening.
Thank you, Andrey. And as Andrey said, he's happy to take any questions. If no one has any burning questions. Yes. So the question was, how does it stack up from an environmental impact point of view?
So if we were able to manufacture the raw materials here, so the powders and the wires, it's actually quite good because you're only using a very small amount of material. So if you compare, let's say, CNC machining to some of these printing technologies, your waste of the material is very small, and you're able to recycle majority of it. And in fact, one of the CRC projects is going to be looking at something that you all might consider strange, but we're going to be taking out metallic implants from patients and turning them back into powder and printing in new types of implant. So in that sense, we're going to be trying to consolidate the whole circle and reuse the materials as much as possible. So often the energy usage is significantly lower. We use less material and we can recycle it. So we do win on a lot of these fronts. And in fact, we, as RMIT, I'm involved in a large funded project, unfortunately funded by European Union, not locally, who are looking at sustainability aspects and understanding the full value chain of the process. But I think this is where we also need to move as a country here.
And so does that mean also, because you're using less materials, less, that it's a lot more affordable to create the part as well?
No, not necessarily yet. So at the moment, I would say we are not winning on the cost. But if you're just printing the same part as you're machining, I would say this is a very bad idea. But if you get us in at the beginning where you have the authority for the design and we can help you redesign your part for additive manufacturing, this is where we can often create better value and we're actually competitive. So there's a number of examples. So If you go, for instance, to RAM 3D, our colleagues from New Zealand, they're demonstrating that they can print parts cheaper than the casting parts. But the casting parts and the printed parts are not identical because they have different wall thicknesses. The parts that are designed for casting are thicker because of the casting, but you don't need the same thickness in the 3D printed parts. And I can give you this kind of examples all day.
Fantastic. Any other questions for Andrey? No, go for it.
Sure.
The bearing that you show, yeah? How does the bear resistance of the material that you put on? How does it get to reach the white part?
So for people that haven't heard, the question was, for the material you put on, how does the wearing go for the new material compared to the original material?
Well, it's actually better. And that has to do with the way we deposit it and the way we can control, again, the heat and the interface between the original material and the new one. Of course, the next step for us is to convince the client that we can use a different material. Because at the moment we are using the same material as the original prescribed. But this is a little bit trickier, right? But again, the future is to try to create ideas of doing things different. And this is where the value add will come from.
Clients always make things trickier. So there's no further questions. Andrei's going to hang around. Sorry, Professor Andrei's going to hang around. Dr. Professor Andrey, His Majesty will hang around if you have any further questions.
You're way to come, worry.
He's more than happy to answer. So please put your hands together for Professor Dr. Andrey.